Hello, everyone. We are the Miniature Coil Gun Group. My name is Jimmy.
I'm Antonio Martinez.
My name is Miriam.
And I am Cody Mitchell.
A coil gun is an electromagnetic accelerator that uses solenoids to launch projectiles. Many subsystems connect to create a magnetic field in a coil to accelerate the projectile. The launcher can be single or multi-staged. Each stage is comprised of an electromagnet capacitor and a silicon-controlled rectifier, also known as an SCR, which serves as a switch. Capacitors are charged with the aid of a bridge converter. The SCR switches to discharge the capacitor, whereby current is pulsed into the coil, thus creating a magnetic field proportional to the current density. This magnetic force is proportional to the force needed to perform mechanical work. From the entrance of the barrel, a ferromagnetic projectile is placed to be drawn by the coil to its center. This LC circuit needs to be critically dampened to create a quick pulse current to induce the magnetic field in the forward direction. Once the projectile reaches the exit of the coil, a sub-circuit switches on to drain current from entering the coil. If this is not switched in time, the projectile can be drawn back in and be suspended at the center of the coil. This is known as the suckback effect.
Here we see the main requirements set for this project. It is going to be a showcase brought into schools. So the dimensions need to be under a 3 foot by 3 foot cube. It needs to be under 65 pounds so it can be carried in. And it needs to be able to shoot a projectile of at least a few grams up to 50 meters a second, so it's something impressive.
Our aim is to pull the projectile to an exit velocity of at least 50 meters per second. Optical through-beam sensors will be implemented to locate the projectile and de-energize the coils to prevent the suckback effect. Sensing and control will be performed with the aid of a microcontroller. Such a device needs to have GPIO capabilities of reading and processing analog and digital data from the optical sensors with enough speed and resolution to limit the suckback effect. It will be tasked with feeding the inputs of the gate driver that will in turn control the SCR. The primary objective of this project is to demonstrate this subset of electromagnetics to upcoming generations to inspire kids and young adults to study electrical engineering. This project is sponsored by the Directed Energy Professional Society, whose vision is to educate future scientists and engineers about directed energy.
This slide covers the block diagram for the coil gun. On the left-hand side, we can see our power supply with a lithium-ion battery supplying a buck converter that goes to our microcontroller. It also powers our bridge converter, which charges up our capacitor banks. The microcontroller is connected to a display, a trigger switch, and each stage of our coil gun, allowing us to fire and discharge coils whenever we need.
On the left side of the screen, we have 6 RLC stages whose current is fed into a magnetizing force equation, which allows us to find the force exerted on the projectile. Using Newton's second law of motion, we can find the acceleration of that projectile. Then we will integrate that to find the velocity. Shown on this slide is the results from the previous slide. It shows an ideal exit velocity of the projectile. Friction will cut down on this, and we do have a device called a chronograph that will allow for accurate measurement of the velocity. Early on, it was decided to use a DC converter to charge the capacitors. After searching for commercially available converters, it was determined their output rating was too low. It would take too long to charge the capacitors. To overcome this, a more complicated device, a bridge converter, was sourced. This will mimic AC, put it through a transformer, and then rectify it back to DC.
This slide shows gate driver will be used between our microcontroller and ACRs to isolate the high voltage and low voltage. Also to drive the ACRs once a signal is received from the microcontroller. This is the bleeder resistor, is used to dissipate the current coming from the capacitors when the projectile reaches the middle of the coil at each stage to minimize the sag-back effect.
The controller of choice for our project is the TVC. It has 6 inputs and outputs to control each stage of our coil gun. This controller meets all of our GPIO requirements, and it's quick acting. This slide showcases the control logic for our project. It is an interrupt-driven architecture meant to turn on and off coils whenever we need. This is the display that we've chosen for our coil gun. It is a 7-inch touchscreen display that allows us to program a GUI to view and analyze important information from our coil gun.
This is the current project build. We have a thin sheet of acrylic with DIN rail supports. On top of this, we have our 6 capacitors mounted in a straight line. To engage and disengage charging and dumping, we have 2 high voltage relays. And to limit the current charging, we have current limiting resistors as well.